Welcome to aminacademy.com. In physics, let us discuss about Kirchhoff's law. What is Kirchhoff's law? Kirchhoff's laws quantify how current flows through a circuit and how voltage varies around the loop in a circuit. We can find both. Kirchhoff's current law, that is the first law, states that the current flowing into a node or a junction must be equal to the current flowing out of it. This is a consequence of charge conservation. In other words, we can say algebraic sum of current flowing to the node is equal to algebraic sum of the current from the node. That means total current flowing algebraic sum is 0. Second one, Kirchhoff's voltage law, that is the second law, states that in any complete loop within the circuit, the sum of all voltage across the components which supplies electrical energy, such as cells or generators, here cell, must equal the sum of all voltages across the other components in the same loop. This law is a consequence of both charge conservation and the conservation of energy. Look at here this closed loop. We have two EMFs, E1 and E2. Here I1 R1 flowing through like I2 into R2 flowing through this, then it goes I3 is coming out. Look at here. Now for the explanation, the first law, look at here this loop. From a given circuit, find the value of I. Here, current flowing through to the node equal to, look at here, this 0.4 towards the node, that is positive 0.4, and towards the node is 0.6 milliamps, and this 0.7, this is 0.7, and coming out of nodes is, this is coming out of node is 0.4, so here, from the node it's a 0.4, out of node is 0.4 and 0.5, 0.5 and 0.2. This is coming out. Suppose coming inside is negative, that is better way, we'll keep coming inside is positive, we'll give it. Coming inside is 0.2 first, 0.2 and 0.6 and 0.7. These three currents towards the node, that is 0.2, 0.6 and that is 0.2, 0.6 and 0.7 coming out from the node, that is from the node is 0.4, that is minus 0.4, this 0.5, and current I, unknown current I equal 0. Now here 0.2 plus 0.6 is 0.8 plus 0.5 is 1.5, 1.5, 0.2 plus 0.6 is 0.8, 0.5 is minus here. Now positives are 0.2 plus 0.6 and 0.7. That here 0.8, 1.5 amps. Here 0.9 minus 0.9, 0.4 plus 1 is 0.9, and I also here minus I equals 0. Here 0.6, 1.5 minus 0.9 is 0.6 minus I equals 0, then I equal 0.6 amps. Therefore, algebraic sum of the current is 0.6 amps. That means it is a positive, so it is come towards the node, final I. Next one, Kirchhoff's second law, the voltage rule or loop rule. The following figure shows a complex network of conductors which can be divided into two closed loops like ACE. Look at here. This ACE, this one loop, and another one loop is ABC, this loop. We are considering both loops together. First, I1 R1, it is this loop. In first loop ACE, current I1 into R1 equal to I have this volts V equal to I1 R1 V1 here plus I2 R2 from here, this loop I2 R2 I2 R2 and plus I3 R3. This circuit is closing like plus I3 R3 is EMF 1. This here, let it be EMF 1. Now this next loop is ABC. With loop ABC here, look at here, I4 R4 I4 R4 voltage passing through is I4 R4, then I5 R5 plus I5 R5 minus, look at this direction is opposite direction, so it is I2 R2. I2 R2 is EMF 2. By using this two equation, we can solve unknown things, because if EMF is given, 2 EMF is given, we can solve the current through current and voltage you can find. Next one, calculate current that flows into 1 ohm resistor in the following circuit. Here 1 ohm resistor is here. Look at here, this we have to say two loops here, EADF, and another loop is EBCF. Here the current flowing through, because we normally are using the direction of the current from negative to positive terminal of the battery. So here the current is splitting in series. First, we can denote the current that flows from 9-volt battery as I1. Starts from here I1 and splits into two current like I2, another current is I1 minus I2, splitting current, because in series currents are here, this here this the current is splitting here, then in parallel this current is splitting into I2 and I1 minus I2 to current sets flows these directions. Here I2 and I1 minus I2. In the junction, according to Kirchhoff's current rule, that is KCR, it is shown below. Now consider the loop EFCBE. EFCBE, this loop. Apply KVR, Kirchhoff voltage law, we get I1 into I2. 1 into I2 because look at here, this through 1 ohm current I2 is passing through, that is here voltage is I2 1 into I2 plus 3 into I1 because this I1 is coming here 3 ohms into I1 plus 2 ohms in I1. Where is 2 ohms in I1? This 2 ohms I1 is passing through 2. Therefore, 3 voltages together is equal to 9. This 9 voltage is splitting like I1 I2 plus 3 I1 plus 2 I1. Totally here I1 3 I1 plus 2 I1 is 5 I1 plus I2 equal to 9, equation 1. Applying KVR to the loop EADFE. EADFE, this circuit, that is, look at here, 3 ohms 3 ohms into I1 minus I2. I1 minus I2 passing through 3 ohms, so 3 into I1 minus I2 plus and minus 1 I2 because this, look at this direction is changing, so negative, so 1 into I2, so the equation is 3 into I1 minus I2 and 1 into I2 equal this here 6 volt, this junction. Then therefore we have, look at here, 3 I1 minus 3 I2 minus 1 I2 totally minus 4 I2 equal 6. The voltage is 6, equation 2. Then solving these two equations by solving simultaneous equation, I1, that is 5 I1, for example here, 5 I1 plus I2 equal to 9, 3 I1 minus 4 I2 equal 6. So we have multiply this first equation with 4 because second equation I have here 4. So 4 multiplies 20 I2 plus 4 20 I1 4 I2 equal 36. Second equation is 3 I1 minus 4 I2 equal to 6. Adding become cancellation, that is 23 I1 equal 42. Therefore, I1 equal 42 over 23, 1.83 approximate, that is A, 1.3 amps. But substitute I1 in any one equation, we get I2 equal minus 0.13 amps. So we got I1 and I2. It implies that current 1 ohm resistor flows from F to E because it's negative. 1 ohm resistance, it's F to E. But direction we are keeping here, but really it flows through this way because we got the negative answer here for I. Next one example for Wheatstone's bridge. Here, the Kirchhoff's law uses for Wheatstone bridge solving problem. What is the value of X when the Wheatstone network is balanced? Suppose here it's a Wheatstone bridge. Here the galvanometer shows 0. That means null current here. This is called a balanced Wheatstone bridge. Here the solution is here. Resistance, this one divided by this one is equal to this divided by this one. That means, look at here, P over Q equal to R over S. Here P is 500, Q is 800, 5 over 800. Then here R is the series resistance of unknown X and 400. That is X plus 400 over 1000 R by S. Then solving this linear equation, we get X equal 225 ohms. We got unknown resistance 225. Next one, meter bridge. What is meter bridge? In a meter bridge, the value of resistance in the resistance box is given as 10 ohm. Suppose, look at here, this, let it be P and Q. P, here P over Q equal L1, the length of this bridge is L1. L1 over, because length in Wheatstone circuit is L1 we are keeping, and divided by 100 minus L1. That is, the resistance is directly proportional to the length of the resistors. Therefore, we are using for meter bridge, we are using here unknown things is L1 and 100 minus L1. So by cross multiplying, P equal Q into L1 over 100 minus L1 by, from this we are using Q equals 10. Q equal to 10 and L1 is 55 by balancing Wheatstone meter bridge. We have L1 over 100 minus L1, 10 in Q equal to 100, L1 is 55, suppose it's given, and 100 minus 55 is 45. By solving this, we have unknown resistance P is given as 12.2. That means if Q is given, we can find unknown resistance P by using meter bridge. Even if Q we can find if P is given, the same procedure. We have done. Please subscribe our YouTube channel.